Hello, in this video I explain static equilibrium. We will look at rigid bodies and analyze if they are in static equilibrium. Static equilibrium means that an object is at rest and remains at rest. Rigid body means that the object is a larger object, not a point-like object. Let's look at an example where we have two forces acting on an object as shown in the figure. We know from previous chapters that we have to look at the forces because forces would cause motion. And we look at the net force, which is the sum of F1 plus F2. To do this, we use the tip-to-toe method. We start with F1 and now we attach F2 at the tip of F1 and we see that we end where we started. That means that the net force is 0 and that means that this object is in force equilibrium. So this object would not start going away because the net force is 0. But what about a possible rotation? If we have two forces pushing or pulling on an object like this, then let's see what happens in this animation. And we see that this object starts to rotate. So we already know that this is not in static equilibrium because it does start a motion. And now let's look at the math. So we identify this as the pivot, and we also know that when it comes to rotation, we have to look at torques. And we have to look at the net torque, which is the sum of torque 1 and torque 2. Torque 1 is minus R times F1. It's negative because this goes in clockwise rotation. Torque 2 is also negative because it also goes in clockwise rotation. This means when we add tau 1 and tau 2 that we add two negative numbers. This means the net torque is negative as well, which stands for a clockwise rotation. This also means that it is not 0 because it's some negative number. That means it's not in torque equilibrium. So this object is not in static equilibrium because it does start to move. Let's look at another example where we have these three forces acting on an object. Let's look at the forces again, and we add all three forces to get the net force. We use again the tip-to-toe method. We start with F1, now we attach F2 at the tip from F1, and now we attach F3 at the tip of F2. We end again where we started. This means that the net force is 0 in this case. But what about a possible rotation? So now we have to look at the torques. We have to pick a pivot point, and now let's just pick the middle. The net torque is the sum of torque 1 plus torque 2 plus torque 3. Torque 1 is minus R1 times F1, is negative because it would pull this object in clockwise direction. And we can also make up a number to calculate with concrete numbers to make it a little bit easier. So we picked 1 meter for the distance between F1 and the pivot. This makes tau 1 to be minus 1 meter times 1 Newton to be minus 1 Newton meter. Torque 2 is 0 because the force goes through the pivot. Tau 3 is the distance of the third force to the pivot times with the force F3. It is positive because this goes counterclockwise. It's also 1 meter away from the pivot, and this makes tau 3 to be 1 meter times 1 Newton equal 1 Newton meter with the values we picked. If we add now the three torques, torque 2 is 0, so we only have to worry about torque 1 and torque 3. And we add minus 1 Newton meter plus 1 Newton meter, this makes 0. So that already tells us the net torque is 0. But if we don't want to work with concrete values, if we want to keep the variables, we can make the statement that the absolute value for tau 1 is equal to tau 3. It tau 1 just has an opposite sign. And when we add the two torques now, we get 0 again. This means this object with these three forces acting on it is in torque equilibrium. But what about if we picked a different pivot point? Because we randomly picked the middle, what if we pick this left side as a pivot? Then the distances to the different forces changes, and now let's do the same math as before. We calculate the net torque, tau 1 plus tau 2 plus tau 3. Tau 1 is 0 now because F1 goes through the pivot. Tau 2 is negative 1 meter times F2 clockwise, and tau 3 is positive, but it's 2 meters away from the pivot times F3. This makes the net torque to be 0 minus 1 meter times F2 plus 2 meter times F3. Here I also included tau 1, which is 0 in this formula. When we compare F2 and F3, we see that F2 is twice as strong as F3. If we substitute now F2 with 2 times F3 in the above formula, we get a new formula. And when we multiply this out, we see that this comes to 0 net torque. So again, it's in torque equilibrium. And now we can make the statement that this object is in static equilibrium because it is in force and in torque equilibrium. And we can write down one condition for static equilibrium. The net force must be 0 and the net torque for any pivot must be 0.